Okay, so one of the keys to be able to do linear regressions is to be able to look at residual plots. Residual plots are basically just that, a plot of all the residuals, a plot of how close the line is to each and every one of the points. And the residual plot, we're actually looking for something that doesn't have a pattern in it. So if you look at this particular graph, this is the residual plot. And if you look here, there's no pattern in there. As you move from left to right, the points bounce back up and down between the line, which means that the line is a good model for this data. Okay? And so a residual plot is a scatter plot of the residuals against the explanatory variables. Again, they help us assess how well a regression line fits the data. If we do not see a pattern in there, it's appropriate to use a line. If there is a pattern in there, then we should be looking for something else, usually some sort of curve. Residual plots, are really important that you interpret them correctly. The residuals need to be small in size, and there should be no obvious patterns. If you look at these two residual plots, there are patterns in both of them. This would not be appropriate to use a linear model for that. So the least square regression deals with the standard deviation of the residuals. Again, this is not a formula that you have to be familiar with, but it is the formula that they use to calculate the standard deviation of the residuals. It's real important that you be able to interpret computer regression output, whether it's from a computer or a calculator. Every program and software will give different pieces of information, and you've got to reach in there and pull out exactly what you need. The three things that you need to be able to find in any regression is the slope, which is usually b, the y-intercept, which is a, and the values of s, which is the standard deviation, and r squared. So you've got to be able to find those four things somewhere within the information here. So on the left here we have what is a common program in statistics, Minitab, and you've got to be able to interpret this information here. So if you notice here, we have coefficients. Okay, well, coefficients are usually numbers that are in front of x, or coefficients can be numbers by themselves. So if you notice the coefficient of the constant, well, if you think about a regression equation, y hat equals a plus bx, this actually is a coefficient. It's the coefficient of no variable, which we call the constant. So this corresponds to the word constant, where this is a coefficient of x, which we all know is the slope. It's the number in front of x. So the slope represents some sort of change, so it represents the change here. So if you learn to recognize the wording here, you realize, oh, this has to be a, and this value here has to be b, has to be your slope. Okay? And the s and the r squared, not hard to find because they use the traditional notation here of s, again, as a standard deviation, and r squared is, in this case, 60.6%. Pretty obvious to find out which those two are. Okay? Well, let's take a look at JMP, which is another calculator, a computer application for calculating stats. If you notice here, the r squared, again, is relatively easy to find because it says r squared there. So that's my r squared value. And this root mean square error is a fancy word that means the standard deviation. So that's the s. So we've got to be able to pick that value out from there. And then once again, now, if you notice here, they use the intercept. Well, that's, if you remember from Algebra 1, that's the mx plus b. That's the b part. But remember, we're dealing with the equation y hat equals a plus bx. So now we got to realize that a is the y-intercept. So that's the 3.50. And the NEA change, again, the word change tends to mean slope. That's the b. So the b ends up being that value, and the a ends up being that value there. So again, it's a matter of interpreting the equation, the wording that's given to you, and saying, aha, this is the value I need. Okay? Some things you need to be aware of when you're doing correlation and regression. They're powerful tools to show relationships between two variables, usually in a scatter plot, but there are limitations there. The distinction between the explanatory and the response variable, the independent and the dependent variable, the x-axis and the y-axis, is very important in regression. It is very important that you actually put the right variable on the x-axis and the correct variable on the y-axis. Otherwise, you can show relationships that aren't really relationships, and you have to be very careful with that. Correlation and regression are only reserved for linear relationships. They do not work with curves. And so that's one of the reasons why our residual plot is so important, because R and R squared only applies to relationships that are linear in nature. You need to be aware of that correlation and least square regression lines are not resistant to outliers or to points that are kind of far away from that. So if you take a look at this data here, there are two outliers. There is this child 19 who seems to have a higher Gazelle score than anybody else. And there's also child 18 who took a long time before his age of the first word. So these are two potential outliers or influential points. And if you look at the residual plot, you can kind of see how child 19 is higher than everything else, and child 18 is to the right of everything. So these are two different types of points. Okay, and we're going to see what the difference is between. Okay, so here's a graph where we did a regression equation with all 19 children, which is the green line in the middle there. Includes all child 19. You notice that R value is negative 0.64. Y hat equals A plus BX. So there's our value for A, and there's our value for B. A is there, and B is there. Notice if I redo the regression equation without child 19, we take child 19 out of there. Notice my R value got considerably higher, and I got a little bit different B value, not much, but and the A value was a little bit different also, which is the slope. Without child 18, notice there was a big difference. So if I got rid of child 18 but left everything else in there, notice here my R value dropped considerably. This is a pretty weak relationship, and both the y-intercept and the slope had dramatically different differences there. So child 19 didn't make a big difference in my answer, but child 18 did. So because of that, we define these as two different types of points. The first point is an outlier that it obviously lies outside the overall direction, but they are usually in the y direction but not the x direction. So in this case, child 19 would be an outlier. And very often that these will not influence our regression equation. An influential point is a point that if you were to remove it, makes a big difference in your regression equation, both in terms of your slope and y-intercept. So child 18 would be influential because remember, that made a big difference in our regression equation. Our slope and y-intercept and our R value all changed dramatically, where child 19, which is an outlier, did not make a big difference. And usually influential points are different along the x-axis. So if you remember, child 18 was far to the right of everything else, while child 19, which is an outlier, was different in the y-axis. It was higher than everything else. So that's kind of the difference between the two different types of points, an outlier and an influential point. One of the biggest things is to realize that just because I make a scatter plot and I find a line that goes through the middle of all the points, that doesn't show necessarily that there is causation, meaning that there's a relationship between my two variables. I can show that there's a relationship numerically, but it doesn't necessarily mean that one is causing the other. Okay? So you have to be very careful and make sure the relationship actually makes sense. Here's an example of a study that was done a while ago. And this is a serious study that once found that people with 2 cars live longer than people who only own 1 car. And they found out that people who own 3 cars was even better. They lived even longer, etc., etc. So they were able to collect some data, they were able to plot the points, and they were able to show that, yeah, the more cars you own, the longer your life lived. Well, why would that not necessarily be a good relationship? Well, the reason that people own cars is probably because they have more money. And people who have more money tend to go to the doctor more often. They can afford to have surgeries or elective surgeries or medicines and etc. They're more likely to take care of themselves. And that's the causation, not because they have more cars, but because they have more money that will allow them to stay healthy. So you have to be very careful. Even though you can show a relationship between the number of cars and how long they live, there's not necessarily a causation. There's not one causing the other on that situation. So these are 4 things you need to be aware about when you do correlation or regression equations in scatter plots.